In the previous class, we were looking at convex functions and properties of convex functions, essentially tests to verify whether a given function is convex or not. So the first test that we saw was that if you take any slice of a convex function, then that slice should also be convex. So basically, if you define g of t to be f of x1 plus t times x2, then g of t is also a convex function. And it's an if and only if condition. And then we saw two tests, the first derivative test and the second derivative test. So if the first derivative, if the gradient of your function exists, then the function is convex if and only if f of x2 is greater than or equal to f of x1 plus gradient f of x1 transpose times x2 minus x1. And this, the right hand side basically corresponds to the tangent plane. And what this is saying is that the function should always lie above the tangent if the function is convex. No matter which point you pick along the curve, the tangent to the curve is always a lower bound on your. Right? And then we saw the second derivative test, which said that if the second derivative also exists, then this must be positive semi-definite. Right? So in other words, the Hessian matrix should be positive semi-definite for all points. And basically, we looked at proofs for these. We saw a few examples of a linear function is positive semi-definite. In case of a linear function, the Hessian is the zero matrix, which is obviously for positive semi-definite, and the quadratic function x transpose ax plus b is positive is convex only when a plus a is positive semi-definite. Right. And we also saw some when f of x equal to e raised to a transpose x is convex. So is this positive semi-definite? It's always positive semi. And again, as a homework, I asked you to prove that the p norm is also a convex function. Okay, so again, you don't necessarily have to use the Hessian to prove that this is positive semi-definite. You can use any approach you want. Sorry, not positive semi-definite, to prove that f is convex. Sometimes you may want to directly use the definition of convexity, but in cases where you can easily compute the second derivative, that generally gives an easier solution. Okay. So there are some sets that are associated with convex functions. So I'm not sure. So one set is the so-called level sets. All right, and this is basically the set of all x in Rn such that f of x is less than or equal to some alpha. So let's call this set S alpha. This is what I'll call the alpha level set corresponding to f. Right? So suppose I give you some function. This is x, f of x. What does the level set look like? So remember, this is a subset of Rn. So in this case, it's a subset of the x-axis. And so I pick a particular alpha, which could be, this is my alpha. Then you look at the set of all points x for which f of x is less than or equal to, which in this case is this particular interval. This is my S alpha. But if I choose a different alpha, I get a different level set. Say this is alpha prime. Then the level set is basically a union of two intervals, two disjoint intervals. And in this particular case, it's a non-convex set. But if I take f to be convex, then what can you say about the level set? Yeah. Okay, so in other words, it's going to be convex. Right? But is the other way true? If all the level sets are convex, I give you a function, and it so happens that all the level sets are convex sets. Does it mean that f is also convex? Okay, so here's the question. If S alpha is convex for all alpha in R, then does it imply that f is convex? Remember, f S alpha is the set of all x such that f of x is less than or equal to R. Just think about examples of functions on R. Suppose that the level set is always a closed interval. Does it mean that f is convex? No. Which, if the function is concave, then would the level sets be convex? They won't. So take a convex function. Right? The level sets are basically these intervals, right? So these intervals basically correspond to the level sets. Now, can you construct a non-convex function for which the level sets are all continuous intervals? Yeah. Okay, construct a concave function, but what would be the level set for this concave function? It's a union of this interval. What do you mean it doesn't have to come? The derivative is 0 density. You want a concave function, right? Okay. Oh, okay. So something which is increasing but concave. So in this case, what are the level sets? Yeah, so they're all line segments. So these are these line segments. Correct? You can construct other examples as well. So suppose I can take a convex function, cut it out at some point, and so this is my f of x. Okay, so basically I cut a convex function at some particular value, and then keep the value keep f of x constant beyond those points. So what would be the level sets in this case? They'll all be convex, right? So this is some value of beta that I take. So if alpha is less than beta, then these are intervals. But then if I take alpha to be greater than or equal to beta, then the level sets are basically all of Rn, all of R. But this function is obviously not convex. This is not. Okay, but how do we prove the claim? So S alpha is the set of all x such that f of x is less than or equal to R. We want to prove that this set is convex. Yep, let's take any x1 comma x2. We know that f of x1 is less than or equal to alpha. F of x2 is also less than or equal to alpha. Just because they lie in S alpha. We want to prove that alpha x, okay, whatever, theta x1 plus 1 minus theta x2 is also in S alpha. Theta x1 plus 1 minus theta x2. We want to show that this is also less than or equal to R. But you know that f is convex. So what can you say about this? This is less than or equal to theta f of x1 plus 1 minus theta f of x2. since f is convex. But this is less than or equal to theta alpha plus 1 minus theta alpha, since x1 and x2 are in S alpha. Any questions? Okay. So this is a very useful property, because let's say that we want to solve convex optimization problems. So what kind of constraints can we handle? We know that we can handle convex constraints. So if I give you constraints of the form f of, say, f1 of x less than or equal to alpha 1, f2 of x less than or equal to alpha 2, and so on. Some fk of x less than or equal to alpha k. If all of these fi's are convex, then what can you say about this overall set? Yeah, it's going to be convex, right? Because the set of all x such that f1 of x is less than or equal to alpha 1, that corresponds to the level, some level set. It's an alpha 1 level set of f1, and the second constraint corresponds to the alpha 2 level set of f2, and so on. And it's an intersection of, so each of these sets is going to be convex, and the set of all x which satisfy all of these constraints is an intersection of convex sets, which is also going to be convex. That's a useful property to keep in. Now, when you plot a convex function, right? Let's say plot, say, y equal to x squared. Okay? This region which is above the function, what kind of a set is this going to be? Okay. Is it always true? So you understand what set I'm talking about, right? You just take any function you want that corresponds to a curve in R2, and all the points above this curve.
Any curve or a convex function?
For a convex function, I want to know what it looks like, but you can plot, you can construct this set for any function you like. There's no alpha, right? It's, you take any function, the region above the curve. So to be more precise, so given f, it is the set of all x comma t such that t is greater than or equal to f of x. So in R, if it's a real valued function, then it's a set of all x comma y such that y is greater than or equal to f of x. So this is what is called the epigraph of a function. Yeah, so the claim is this is convex. Okay, now let's suppose I have a non-convex function. Take any non-convex function of it. We'll prove that later. But this is going to always be convex as long as f is convex. But suppose I take a non-convex function, right? What will the epigraph be? Will it be a convex set? Not necessarily. Can you construct a non-convex function for which the epigraph is convex? Hull of what? Again, you can't use the word hull in isolation. The convex hull of some set.
So like this t greater than or equal to f of x also includes t equal to f of x.
Yes.
And so that particular part is not convex, the whole thing cannot be convex.
Yeah. So in fact, it's a necessary and sufficient condition. If f is convex, then the epigraph is convex. If f is non-convex, then the epigraph will also be non-convex. The claim is that the epigraph is convex if and only if the function is convex. That's a necessary and sufficient condition. So how would you prove this? Again, just use the definition of convexity. So suppose that f is convex. You want to prove that the epigraph is convex. So take any 2 points in the epigraph. So pick an x1, t1 and x2, t2 that lie in the epigraph. You want to prove that this is also in the epigraph, but this is just theta x1 plus 1 minus theta x2, theta t1 plus 1 minus theta 2. For this to lie in the epigraph, it must be the case that the right hand side is greater than or equal to f of this particular. So f is convex. This is less than or equal to theta times f of x1 plus 1 minus theta f of x2. But what do you know about t1 and t2? They're in the epigraph. So f of x1 is less than or equal to t1 and f of x2 is less than or equal to t2. This is less than or equal to theta t1 plus 1 minus theta t2, which means that this is also in the epigraph. And you can prove the other way around similarly. So if the epigraph is convex, then f also should be convex. Just by looking, you just choose the point where t equal to f of x. Choose points where t is equal to f of x. That corresponds to the function itself. And then evaluate, just use the definition of the epigraph and convexity. Now, just like the epigraph, you can also define what is called the hypograph of a function. Which is simply the set of all x such that comma t such that t is less than or equal to f of x. If you have a function f, then the region above the curve is called the epigraph, and the region below the curve is called the hypograph. If f is convex, obviously the epigraph is convex. The hypograph is non-convex. But what if f is concave? The hypograph would be a convex set. The epigraph would be non-convex. So in our definition of convexity, what we showed was that if you take a convex combination of 2 points and evaluate the function at this particular convex combination, then the function value is always below the linear combination of the function. So basically what we showed was that f of theta x1 plus 1 minus theta x2 is always less than or equal to theta f of x1 plus 1 minus theta f of x. Now, what if I take a convex combination of more than 2 points? So you look at f of theta 1 x1 plus theta 2 x2 plus some theta k xk, theta 1, theta 2 up to theta k being greater than or equal to 0, and summation I equal to 1 to k theta I equal to 1 versus I equal to 1 to k theta I fi f of xi. Can you claim that this is always true? Okay, why is this true? To prove this inductively, you know that it's true for k equal to 2. Assume that it's true for up to k minus 1. So what would the induction step be? So we're given that f of theta 1 x1 plus theta 2 x2 and so on up to theta k minus 1 xk minus 1 is less than or equal to theta 1 f of x1 theta k minus 1 f of xk minus 1. This is given to you. What you want to show is that f of theta 1 x1 plus theta 2 x2 k minus 1 xk minus 1 plus theta k xk, this is less than or equal to summation theta I f of xi. But I mean, there's a slight difference between this and this. In this case, the summation of the theta 1, theta 2 up to theta k minus 1 is equal to 1. Whereas in this case, theta 1 plus theta 2 up to theta k is equal to 1. So how would you prove the induction step?
Divided by 1 minus theta k of the k minus 1.
Okay, so theta k minus 1, what do you want to multiply and divide by?
No, like basically we can use the part that is convex. So we can
Okay.
split it into k minus 1 terms and 1 term.
Okay,
So for the k minus 1 terms, we can multiply and divide by 1 minus theta k, so that we can split them.
okay, so let's group them into two terms. One, the first, which consists of the first k minus 1 terms, where I can use this particular step, plus I have this one single term that is left over. Okay, all right, let's suppose that I can do this. Now what would I do?
This induction, it doesn't satisfy the definition of convex scaling
Which one?
because the theta goes up to 1, so it's no longer the definition of.
Correct, so I need to do something a little more.
Other factor that
Okay, what would you multiply it by?
say some factor,
by some lambda 1, lambda 2.
Correct. What would be the lambda then? 1 minus theta k, right? So theta 1 x1 plus theta 2 x2 up to theta k minus 1 xk minus 1. Let me multiply this summation and divide by 1 minus theta k. Okay, so this whole term is going to be my x1 prime, and this term is my x2 prime. Now I can just use the definition of convexity, right? I have f of 1 minus theta k x1 prime plus theta k x2 prime. So this is less than or equal
K equal to 2.
correct, whatever. So this is 1 minus theta k f of theta 1 by 1 minus theta k x1 plus theta 2 by 1 minus theta k x2 theta k minus 1 xk minus k plus theta k f of xk. Great. Now can I use the induction step on this? Do the coefficients all sum up to 1? You're convinced? Right? Because all the theta I sum to 1, theta 1 up to theta k. So if you leave out theta k, theta 1 plus theta 2 up to theta k minus 1 must sum to 1 minus theta k, which is exactly what you divided by. Now use the U star. So this is less than or equal to 1 minus 1 minus theta k, theta 1 by 1 minus theta k, f of x1 plus theta 2 by 1 minus theta k, f of x2, so on theta k minus 1 by 1 minus theta k xk minus 1 plus theta k f of xk Okay, so it's fairly straightforward. But let's look at this statement once again, right? You're saying that theta 1, theta 2 up to theta k should be greater than or equal to 0. It's a convex combination. And the summation of all theta I should be equal to 1, right? What does this correspond to? The theta vector. Yeah, it's a probability mass function, right? So then this theta 1 x1 plus theta 2 x2 up to theta k xk, what does it resemble? It's an expectation, right? So this is just expectation of x, where the random variable x takes value x1 with probability theta 1, x2 with probability theta 2, xk with probability theta k, right? But now what is the right hand side? It's expectation f of xk. Yep. So you've seen this before. This is just Jensen's inequality. So although we proved this for finite convex combinations, or in other words, probability mass functions, this in fact holds true for any general random variable, potentially even continuous. All right. So if you've taken the information theory course, then you would have seen Jensen's inequality. But it's okay, even if you've not seen it before, this is a very useful inequality to do. And there are a lot of several consequences of this. You can prove many things just using Jensen's inequality. So let's see one particular example. Well, effectively, using Jensen's inequality is the same as using convexity of a particular function. So let's start with something that you've seen before, right? Which is, suppose that A and B are real numbers, let's say positive real numbers. What can you say about square root of AB versus A plus B over 2? Yeah? Less than or equal to, right? Square root of AB is less than or equal to A plus B by 2. This is the AMGM inequality, right? Can we prove this using whatever, convexity or Jensen's inequality? Let me take log on both sides. Okay, so saying this is the same as saying half log AB is less than or equal to log A plus B by 2. Or if I rearrange, log A plus B by 2 is less than or equal, or negative log A plus B by 2 is less than or equal to negative log A by 2 plus negative log B. And what do you know about minus log? Minus log x is convex, right? So this is f of A plus B by 2 less than or equal to half f of A plus half f of A. This is just definition of convexity or Jensen's inequality, whichever way you choose to look at it. Using this, you can prove the Cauchy-Schwarz inequality, or more generally what is called Hölder's inequality. So let's take any vectors x and y, and PQ strictly positive, such that 1 by P plus 1 by Q is equal to 1. Then is less than or equal to the P norm of x times the Q norm of y. We also need, I'll take P to be strictly greater than 1. So even before this, let's look at the previous AMGM inequality. Can you slightly generalize this? So how did you obtain this? Well, just by looking at convexity of the log of minus log function, right? And we looked at a very specific convex combination, half and half. Suppose I took some other convex combination, then what kind of an inequality would I get over here? Okay.
1 by P times A plus 1 by 2 times.
Sure. So you could say that if you want to, let's say you could use one P and Q, or let's say I take a theta between 0 and 1, then effectively I can say that A power theta times B power 1 minus theta is less than or equal to theta A plus 1 minus theta B. Okay, or in other words, A power 1 by P times B power 1 by Q is less than or equal to 1 by P times A plus 1 by Q times B, because 1 by P plus 1 by Q is equal to 1, and 1 by P and 1 by Q are also between 0. Okay, can I use that to prove this? Sorry? Take log of what? This one? Which one? This particular quantity. Okay. And then So maybe let's start with the easier case where P and Q are half. Okay, so that just comes down to Cauchy-Schwarz. So the left hand side is just the inner product. The right hand side are just the norms. The 2 norm of x times the 2 norm of y. Right? Okay. So let's suppose I want to show that summation I equal to 1 to n xi yi is less than or equal to square root yi square, right? So suppose I take xi square by equal to 1 to n. Okay, so this is my A and my B is yi square. If I just use the AMGM inequality, what would I get? So you get xi. What would the left hand side be? Square root AB, which is what? It's mod xi mod yi by norm x times norm y less than or equal to right hand side a plus b by 2. So xi square plus yi square by 2 times, sorry, xi square by norm x square plus yi square by norm y square into half. Now what happens if I take summation over all possible I? Mhm. Right? What is the right hand side going to be? 1, right? So summation of all of this is going to be 1. This is going to be 1. So 1 plus 1 is 2. The 2 and 2 cancel. Just multiply both sides by norm x times norm y. And that just gives you Cauchy-Schwarz. So you can derive it just using the AMGM inequality, nothing more. So as a homework, prove Hölder's inequality. So let's stop here.